online course titled as DSC Practical Interpretation with examples for polymer development, and it's presented by Jeffrey Jameson. Hi, Jeffrey. How are you doing?
I'm doing well, thank you.
Well, thank you, Jeffrey. It's good to see you. I'll get back to you in a couple of minutes. As of now, I will share some tips with our participants on how to interact with us during the presentation. Dear participants, let's take a closer look at your attendee panel, which has several interactive and useful features. The most important would be chat facility. Please feel free to use chat facility to address any kind of technical issue related to web or audio. You can use this chat facility to address your comments or questions, but please note that your questions will be held with us until the end of the presentation and will be answered during 30 minutes of question answer session. Finally, if you use your telephone to listen to this presentation, we remind you that you need to dial the audio pin which is displayed in attendee panel. Now, ladies and gentlemen, before we start our presentation, let me brief you a little bit about our expert. Jeffrey A. Jameson is the engineering manager and the partner at the Madison Group, an independent plastic engineering and consulting firm. Jeff is a proven plastic professional with more than 30 years of experience solving problems and addressing opportunities related to plastic materials. He specializes in failure analysis, material identification and selection, as well as compatibility, aging, and lifetime predictions studies for thermoplastic materials. Jeff has performed over 5,000 investigations both for industrial clients and as part of mitigation. He regularly presents live seminars and webinars covering a wide range of topics related to plastic failure, material performance, testing, and polymer technology. Jeff is a graduate of Carroll College and the Malviki School of Engineering. So that was all about our expert. Jeff, you can take over from here.
Thank you very much for that introduction, Maya. And welcome everyone to today's presentation on differential scanning calorimetry. Over the next hour, hour and a half or so, it's my goal that you'll become more familiar with how differential scanning calorimetry can be used to identify and to characterize polymeric materials, that you'll gain insight into how composition and polymer structure can be evaluated analytically using this technique, and understand how DSC experiments are run and how to review and interpret the data. So we're going to walk through the fundamentals of DSC, differential scanning calorimetry. We're then going to talk specifically about its application to polymeric materials, look through some test methodologies, thermogram interpretation, and throughout talk about real-life case studies. Okay, let's talk a little bit about the fundamentals. So differential scanning calorimetry, DSC, what is it? Well, it's a thermal analysis technique that measures how a sample's physical properties change over time and temperature. So all thermal analysis measures some types of properties of the material and how they relate to temperature or time. Thermogravimetric analysis, for example, measures thermal stability or weight. Thermomechanical analysis looks at glass transitions, measures modulus as a function of temperature. And differential scanning calorimetry, DSC, what we're going to focus on today, gives us a whole range of materials by looking essentially at the heat flow of the material. So when we talk about thermal analysis techniques, there's four principal techniques: DSC, thermogravimetric analysis, or TGA, dynamic mechanical analysis, DMA, and thermomechanical analysis, TMA. And what some studies that have been done show that DSC is by far the most commonly used technique to evaluate polymeric materials. Of these four thermal analysis techniques, DSC is the most commonly used because it provides such key information. DSC measures the temperatures and the heat flows that are associated with thermal transitions in materials, polymeric materials specifically, as we look at today, as a function of time and temperature while under a controlled atmosphere. What we're measuring is the difference in the amount of heat required to increase the temperature of a sample and keep that sample at the same temperature as a reference. That's what we're measuring. Again, we're measuring the amount of heat, energy required to keep what is going to be a sample and a reference at the same temperature. We'll look a little bit more at that just briefly, but what that looks schematically. So DSC measurements provide both quantitative and qualitative information about those physical and chemical changes that take place, specifically that involve endothermic or exothermic processes, transitions within the material that are exothermic or endothermic. Either the heat has to flow into the sample or heat flows out of the sample, or those transitions that involve a change in heat capacity within the material. So the kind of things we're going to be talking about over the next hour or so are going to be the things that DSC measures, the things we want to evaluate, like glass transitions, phase changes, melting points, crystallization and crystallinity, product stability, pure kinetics, oxidative stability. These are the kind of things, the kind of experiments that we can run with DSC, the type of information that it can provide to us. So the key aspect of the DSC, the real heart of that unit, is going to be the heat system, the thermocouple. And so this is just one model of DSC, but they all share some things in common. And specifically what we're looking at is this area right here, okay? You'll see we have two pans here. One is going to contain our sample, and the other is going to contain basically just a reference pan, an empty pan, if you will. We're going to talk more about pans later, but contains an empty pan. So if we look at it here we have our sample. It's enclosed in this pan. Here we have that empty pan. And essentially what we're doing is we're measuring the heat or energy required to come into this system to keep our sample at the same temperature as our reference. For example, as we undergo a melting point, okay, we have to pump more heat into that sample in order to melt the crystalline structure of the material, all while trying to increase the temperature within our sample to match that of the blank or the reference. Okay, so it takes more heat within that. If we undergo, let's say, crystallization, as we crystallize the samples, that actually gives off heat, and actually then our energy is going to go down. So again, we're just comparing the amount of energy that flows into here, into our sample, compared with our reference. And I don't want to belabor that point, but I want you to understand what we're measuring with DSC. What we get is a thermogram. That's what the graph is called that we get from a DSC. It's called a thermogram. Okay, and this shows some of the transitions, not all, but some of the more prevalent transitions that we might see. This is a sample of polyethylene terephthalate, and as we heat the sample, and we're going to talk more about these experiments later, but as we heat the sample, we undergo a change in heat flow. And so we see this S-shaped curve. That's a glass transition. Then as we continue to heat the sample, we're actually going to form crystals within that PET material, and that's this exothermic transition. One important point I want to make is that anytime you look at a DSC curve, you want to note this: which direction is endothermic or exothermic, up or down? By convention, that typically is the instrument manufacturers kind of have different ways to think about it. I typically use TA Instruments equipment, and by convention, they usually have exothermic going up, endothermic going down. And so that most of the graphs that I'll show today have that orientation, but that's anytime you look at a DSC curve, you want to be looking for this to be identifying where, which direction is endothermic and exothermic. Okay, so we have this exothermic transition, then we undergo an endothermic transition associated with melting of the material. As we cool the sample down, another exothermic transition associated with recrystallization of the material. And again, we're going to dive into these a little bit more to talk about what information we can get from them. But those are the basic things. Typically, I say, we're going to have heat flow on the y-axis and temperature on the x-axis. But there are some experiments where we plot some different things. But that's our DSA thermograph. So applications for polymeric materials. What can we do? What information can we obtain through DSC for polymeric materials? We can get material identification. So polymer identification, polymer type differentiation, understand whether we have a copolymer or a homopolymer. We can evaluate polymer blends. We can even look at some polymer additives. We can look at the condition of the material, whether the material has been degraded. In some cases, we can understand things about the purity of the material. We can look for contamination. We can understand its oxidative stability. How far along is our antioxidant package been consumed? We can also look at material properties, heat history, look at things like crystallinity, the thermal history, specific heat capacity. If it's a thermoset, we can look at heat of reaction, reaction kinetics, and ultimately degree of cure. So there's a lot of different applications. This is why DSC is the most commonly used thermal analysis test technique for polymeric materials, because it provides the opportunity for a lot of information. So let's run through some of these. So material identification, okay? Like I showed before, there are different transitions that the material is going to undergo. And again, just so you see it, here's our EXO up. They'll be on all thermograms, ought to have that information. Anyway, most fundamentally, what we can understand about our material is if it's semi-crystalline or amorphous. Amorphous materials have a totally jumbled structure. They have no crystalline domains, and as such, the only transition they're going to undergo is a glass transition. Semi-crystalline materials have some amorphous content, but they also have crystalline content. So as such, they're going to undergo both a glass transition and a melting endotherm. So we can understand, again, just simply by looking at the materials, the results, I should say, do we have an amorphous or do we have a semi-crystalline material? Now, I've got this plotted this way. And again, understanding, what we've got, to those materials. So again, just some semi-crystalline versus amorphous materials and what you can expect. So in the semi-crystalline group, we would likely see a melting endotherm, and we should also see at some level a glass transition associated with the amorphous content. And with the amorphous material, we're only going to see that glass transition. Okay, so I showed before, let's look at that. I showed before kind of these two transitions, the glass transition and the melting endotherm, looking like they're on the same order of magnitude of intensity when it comes to heat flow. Well, that's really just a scaling issue. If we really look at that, they are not. A melting endotherm typically is much, much stronger. We get a much bigger change in heat flow than we do with a glass transition. The glass transition much, much weaker in terms of its response. So again, don't be fooled by what I showed you there. That glass transition is relatively weak, and that's going to play a role. We need to understand that when we're starting to think about contamination. More about that in a little bit. So again, as we go through the melting point, we understand that endothermic energy is required to get there. Exothermic transitions, energy is given off. And that, again, is why we need to understand a little bit of how that instrument works. And the heart of it is that thermocouple measuring the heat flow. So the melting point, okay? What is the melting point? We're going to understand that by DSC where it is, but what is it? Well, it's a transition that occurs in semi-crystalline polymers when the polymer chains fall out of their crystalline structure and it's instead become a disordered viscous fluid. It just is that, when that crystalline structure actually melts, okay? The transition from crystalline to liquid state is not sharp as it is for small molecules. If we look at the melting point of, say, an organic material, monomer, we're going to see a very sharp melting point, okay? With polymeric materials, because there's a variation in molecular weight and the organization of the crystals may not be the same across the entire polymer. They're not as organized, they're organized differently. We're going to get this broad melting point, okay? Amorphous thermoplastics don't melt. Thermoset materials don't melt. And that melting point can actually be used to differentiate or identify materials and also understand something about the thermodynamic characteristics of the polymer. Okay, so here's polyethylene, very simple molecule. And if we look at that, again, what are we looking at here as we evaluate the heating run here? we see that we've got a melting point. Now, the melting point for polymeric materials, by convention, is the maximum, well, I guess it would be the minimum of that peak, okay? That's the melting point of the material. The area underneath that curve is called the heat of fusion. So that's reported in joules per gram. And then typically there's an onset value that is also reported, although that's a little bit less used. Again, the melting point for polymeric materials is going to be that minimum on the melting endotherm, okay? And just to kind of show you again what I was talking about, if we're analyzing, again, a polymeric material, relatively broad peak, and we look at the melting point as that minimum, if we're running other things like organic materials, organic monomers, or in this case, if we're running like a solder, here we have indium, which is used to calibrate the instrument. In that particular case, the melting point of the material for those materials is typically taken by convention as the onset. And you'll see that there's not a big difference. The onset is at 156.39, and the peak is only 1 degree later. Here, our onset is 121.94, and it's about 7 degrees higher. Again, just a measurement of the broadness of that endotherm, the melting endotherm. And that is, again, because typically with metals or with organic monomers, the crystalline structure is much more defined, much more uniform. Molecular weight is not an issue. All those things play a role in how broad the melting point of that polymeric material is going to be. And what I said before was that we could identify materials based upon their melting point, okay? And that certainly is true. Different polymeric materials have some different melting points. Now, some overlap, but again, to a large degree, they're very, very different in terms of their melting points. In fact, nylon 6 and nylon 6,6, you know, my first technique I usually use in the analysis of polymeric materials is Fourier transform infrared spectroscopy, or FTIR. Well, FTIR doesn't do a good job when the molecules are relatively similar, like we have here with nylon 6 and nylon 6,6. So structures are pretty similar. So the FTIR spectra are very similar, but those two materials have very different melting points. And so nylon 6 melts at around 221, nylon 6,6 around 261 degrees. So again, we can use that to kind of supplement our FTIR. Again, FTIR is a great place to start, but it doesn't give you all the information in all cases. So DSC starts to fill in some of those gaps, helps us with that. And so again, what can we do with that? So here we have two more materials that are very similar. PEEK, polyether ether ketone, and then polyether ketone ether ketone ketone. Again, benzene rings, ether linkages, ketone structures, very, very similar. FTIR is going to be comparable, but they give us different melting points so we can understand what material we have. Again, very similar materials, differentiated. Here's another example, polyacetal copolymers and homopolymers. Copolymer has a very, very small amount of this ethylene functionality that is in the molecule, changes the structure a little bit, gives it some different performances. But again, those two structures are very, very similar. FTIR, our kind of first go-to technique, cannot differentiate them, but they have different melting points because of that structure. So DSC can be used. In the same way with homopolymers and copolymers, we have polypropylene, okay? With polypropylene, it comes in a variety of different configurations, a homopolymer, a block copolymer, a random copolymer. And we can then, by the melting point, we can look at those materials and see what's going on. For example, the homopolymer going to have the highest melting point, around almost approaching 170, and it's a single endotherm. The block copolymer, okay, the block copolymer is going to have blocks of propylene, but also some blocks of ethylene. And those ethylene segments are also going to melt. And so we've got a melting point around 119, representing the ethylene functionality, and that little lower melting point, that little bit of reduction closer to 165 for the propylene segment. Okay. And then if we've got a random copolymer, that melting point shifts because of the disruption in how those crystals form because of the ethylene, propylene mixed together randomly, and that melting point drastically reduced. Again, very, very useful for being able to identify that where FTIR is not going to be helpful. Another example is that we may have an unknown elastomeric material. FTIR spectrum matches pretty well with a thermoplastic olefin, which is a combination of EPDM and polypropylene, as well as EPDM. Really, we can't tell the material that we have there by FTIR, but when we run DSC, we have a melting point. We get a melting point about 151. That's what we expect, again, for the polypropylene that's present in that EPDM, as that thermoplastic olefin. Again, what I'm showing you is a variety of different ways, and there are more than this. Hopefully that'll kind of stir your mind as to how you can use DSC to differentiate some materials that might not otherwise be differentiated by test techniques like FTIR. So we've been talking about melting transitions, melting endotherms. Well, again, the other primary transition, if we're talking about then an amorphous material, is going to be a glass transition, which is a change in the heat flow. Okay, it occurs within amorphous polymers and in the amorphous segments within some semicrystalline polymers. Now, oftentimes that glass transition is relatively weak in some materials. For example, polyethylene, it's so weak because it's a very crystalline material. Polypropylene, kind of the same way. It's hard to see that glass transition. But they are present for semicrystalline materials representing the amorphous state. It's the temperature region where the polymer segment transitions from that hard glassy material to a soft rubbery material. That's why we call it a glass transition. That makes some sense. Again, it takes place in both thermoplastic as well as thermoset events. So thermoset plastic will also have a glass transition. Remember that there is no phase change as a result of passing through the glass transition. So a little bit like we saw for semicrystalline material, the glass transition now, instead of the melting endotherm, can be used to possibly identify amorphous materials, although some of those materials have some glass transitions that are a little bit closer overlapping to each other, and that peak is not quite as sharp. Something else we can understand through evaluation of amorphous materials with the glass transition is going to be whether we have a single phase material, which is called an alloy, or whether we have a dual phase, which is more properly known as a blend. Here's a great example of a very common material, polycarbonate ABS. If we have a single glass transition, that means that these two materials were put in such a way and mixed together and put in at the ratio that there's a single phase. If those two materials, those two polymers were miscible in the way that they were mixed at the concentration that they were mixed at. Okay, single phase, one glass transition. Okay, if we see two glass transitions, one associated with the ABS, one associated with the polycarbonate segments, now we know that we've got two phases. Now that's not always extremely important to understand, but again, it's some more information that we can take away about our polymeric material. So we can also be able to understand some things about polymer-based additives. So here we have some samples. Sample 1, sample 2, both are based upon PBT, again, by the FTIR. But we also see some additional absorption bands that are suggestive of PTFE, polytetrafluoroethylene, which is commonly added to polymeric materials as to change the lubricity of the material, to change the coefficient of friction, to change the wear properties. So if we look at a sample of PTFE, pure PTFE, we can understand the heat of fusion of that material. That's, again, 100% pure. This is the second heating run, and we're going to talk about that a little bit later about what that means. But this is the second heating run, which allows our material kind of to be optimized for crystalline state. And we see that we've got about 28 joules per gram. That's required. That's the energy required to melt that material at 100% pure. Okay. When we have our PBT, PTFE mix, we can see that here we've got about 7 joules per gram, which would suggest that we've got roughly about, 1/4, about 25% PTFE in that PBT. Now, there's other ways to come at this. TGA would be a great way to analyze this also, but again, another piece of information that you can get off of the DSC. Material condition is another aspect that we can see. So one of the things that DSC can do is identify the presence of contaminants in a material. So here we have PBT contaminated in the ABS, and this is a great example of the variation in those intensities of melting endotherms versus glass transition. And so here we see that the PBT is a contaminant. And what we ultimately figured out is it's about 20% PBT. There was a lot of contamination, but you'd never guess that if you looked at this result. Here's our glass transition, looks relatively weak. Here's our melting endotherm, looks pretty strong. You'd guess that this is mostly PBT, perhaps with some ABS contamination, but it is the opposite way around. The good news is that contamination just stands right out. It jumps out at you. So you can identify, in some cases, contamination in materials. So let's look at this little matrix here about what you can do. If our base material is semicrystalline and our contamination is semicrystalline also, well, it depends upon the concentration. So if you've got something at 1 or 2%, you may not see it. A contaminant 1 or 2% in your base material, you may not see it. If our base material is semicrystalline and our contaminant is amorphous, well, that amorphous peak is relatively weak, very, very weak. It really is almost impossible to find. But if we have an amorphous material and we have a semicrystalline contaminant, which is the case we showed here, well, that's pretty easy to find. If we've got amorphous base material with an amorphous contaminant, again, it's going to depend on the concentration. How much of the two materials do we have? Again, contamination is something else we can find by DSC. Some people do some work with purity. This is more commonly done for monomeric materials, sometimes for pharmaceuticals. Not so often done with polymeric materials, but again, I wanted to give you the concept, and that's that if we've got a very, very pure material, our melting point, our onset of our melting point is going to be relatively high. The melting point will also be higher also, but we're looking at the onset now. The onset will be high, and our peak will be deep and narrow. The more contamination we have in our sample, okay, that melting point is going to go down, the onset is going to be reduced, and we are also going to get much more broad, okay? Again, it's not done a lot with polymeric materials. I have not really found an application for it, but again, that's just another piece of information that's out there. DSC can be looked at the plasticizer effect. So here we have an example of some polyvinyl chloride, some PVC resin. We have some that's not plasticized, some at 10% dioctyl phthalate, and some at 20 dioctyl phthalate. So plasticizer changes the physical properties of that PVC. It takes the PVC in a non-plasticized state, that's something like a rigid PVC pipe, and turns it, once we add plasticizer to it, to something more like a power cord. It's very, very flexible. Okay. What happens is that the increased level of plasticizer changes those physical properties, but that's really tied to it that it also reduces the glass transition temperature of the material. Okay, and we can see that our unplasticized material for PVC, glass transitions around 76. As we add increasing levels of dioctyl phthalate, we drastically reduce the glass transition temperature of the material. So, excuse me, there are some other ways to evaluate this quantitatively. It can be difficult by thermogravimetric analysis, but you can do some things with more chromatography, things like that. But the DSC gives us a nice indication. So if you can establish what is kind of a calibration curve, you could, in theory, then come back and understand how much plasticizer is in that material. And certainly you can understand whether it's plasticized or not by how, where it is with the glass transition. So again, understanding additives within the material. Degradation is also something we can get a clue about with DSC. So here we had some failed parts, and we also then had some molding resin. This is polycarbonate. And the polycarbonate the pellets give us a glass transition of about 149, right where we expect for polycarbonate. our failed samples were down about 143. And that suggests to us that that reduction, that 6-degree reduction, is pretty significant. That suggests that we've got something changing about the material. A good chance it's going to be molecular degradation. They've either been degraded during the molding process or during field service. We did a melt flow rate to come back, and then we found that was in fact the case. Much higher melt flow rate on the failed parts, which correlates with that reduction in the glass transition. So we can look for changes in the glass transition or the melting point to give us some information about potential degradation. You'd certainly not want to, let me just summarize, or another point to that, you certainly wouldn't want to use this only test to say that the material is degraded. There could be other things. There could be contamination. There could be some other things that reduce that melting point. But it's a red flag during your analysis that says, hey, I better make sure I'm looking at other things like the molecular weight of the material. Kind of a different test to all the rest. This is one that uses kind of a different type of experiment. Is going to be oxidative induction time, or OIT. And basically what we do here is we heat the sample up, and here I've got temperature kind of thrown in. We're going to look at time on the x-axis, but I've also got temperature so we can see what happens. We're heating the sample up in a nitrogen atmosphere, and then we hold it isothermal, and then we turn on oxygen or air, but very commonly oxygen. And then we measure the time from this point to that point. Now, again, we would know that this is at almost 8 minutes. This is a little over 8 minutes. So we basically got 11 minutes between when we turn the oxygen on and when we start to see this endothermic shift. This represents oxidation of the polymer. The polymer undergoing a chemical reaction with oxygen, which means that our antioxidants have been consumed. This is the induction time. This is the time that exposure to oxygen at elevated temperature has consumed all of our antioxidants. So we can get a picture of the material if we understand what it was like right after molding, and we understand what it was like after, say, 2 years in field service. How are we doing? Have we consumed all the antioxidants? Do we still have antioxidant left? We can get a good feel for the material. So again, it's a different experiment where we heat dynamically under nitrogen to get to an isothermal temperature. We hold that isothermal temperature for a couple of minutes, and then we turn on the oxidizing atmosphere. So here's an example. Here's our 2 parts that came out of the field. One in a mild environment, and we still had, this is the time zero now, is we re-zeroed the curve. This is after the air is turned on, the oxygen is turned on, and we get about 13 minutes before the polymer starts to react. Our failed sample starts to oxidize immediately, and so that tells us again that the antioxidant has been totally consumed, and that this material is not being protected, and it's another way to understand whether the material has been degraded during field service, and by what mechanism. We can also, again, get a red flag. It's not necessarily a smoking gun, but a red flag whether the material is got molded in stress in it or not. And that's if we have this, you can see that the material starting to undergo, as it goes to the glass transition, this endothermic shift downward. I think I said this was an endothermic shift. I apologize. Oxidation is an exothermic shift. I apologize for that statement. This would be exothermic, that transition, that reaction with oxygen. But here, as we're undergoing the glass transition, that endothermic shift, we see this kind of phase upward. That kind of upward shift then is the material actually the molecules reorganizing themselves, and it's a clue that this material has possibly been molded in such a way as there is molded in residual stress. Let's look at some material properties now. So one of the key things about semi-crystalline materials is the crystallinity. Okay, and so we certainly want to look at that. So here we have a sample of PBT. Mentioned this earlier, but we get the melting point of the material. That's the peak, but we also get, okay, that enthalpy, that area under the curve. That's the energy required to melt the material. The higher that number, the more crystalline that material is, okay? And so we can see that different polymeric materials have different levels of crystallinity. High-density polyethylene, for example, is a relatively crystalline material. Of most commonly used polymers, it's probably the highest level of crystallinity. With some grades at 220, even higher joules per gram to melt the material. Again, the higher that number, the more energy we need to put into that, the more crystalline the material is. Okay, polyacetal, homopolymer, another relatively crystalline material. Polypropylene, again, getting a little lower, but still relatively high. Then we get to the other end of the scale, PTFE. In this particular case, about 18. Polyphthalate, 24. PEEK, 32. Much lower. And so, and in the middle, PBT and nylon 6,6. So again, we can understand how crystalline a particular grade of material is. This is extremely effective for looking at high-density polyethylene. We want to understand two things about polyethylene typically. What's the molecular weight of the material? We typically get that through melt flow rate. And we want to understand crystallinity, which can either come through doing density or specific gravity testing, or I think more effectively by doing DSC. And you get an actual number to understand that crystalline level. So again, crystallinity is something we certainly want to look at with our semi-crystalline material. And again, differentiating a variety of materials. So here's a great example of variation in that, and that's what is a relatively large difference between high-density polyethylene and low-density polyethylene. For one thing, high-density polyethylene has a much higher melting point, but you'll also see, again, depending on the grade, it's going to have a much higher heat of fusion. Here, 220 versus around 91 for this grade of low-density polyethylene. So again, differentiating our materials, where again, FTIR is not going to be a great way to tell these apart. DSC is going to tell us which we have and also give us insight into the crystallinity. Okay. Here we have, in terms of crystalline structure, DSC can give us an insight into maybe why the material is, how crystalline it is, and then the structure can, together with the DSC can tell us why. So here we have the comparison of nylon 6,6 versus polyphthalate. Certainly polyphthalate has a higher melting point, but it also has a drastically lower level of heat of fusion. Enthalpy is much lower. It's a much lower crystalline state. When we look at it, well, we've got this benzene ring, this relatively rigid structure that doesn't lend itself to folding back on itself to form crystals. Where with nylon 6,6, we've got a lot of olefinic content. And so that actually does tend to come together quite nicely to form crystals. In terms of that, again, just understanding crystallinity, if we've got a polymer with linear structure, that tends to promote crystallinity. Things like high-density polyethylene and polyacetal have a relatively simple linear structure. Again, they have the highest level of crystallinity. If we've got stereoregularity, that tends to promote greater crystallinity. So things like atactic polypropylene, atactic polystyrene, they're amorphous, but the isotactic and syndiotactic versions, because they're more stereoregular, they're semi-crystalline. Bulky side chains, like we saw in the previous example with the polyphthalate, again, they tend to impede the formation of crystals. Polyvinyl chloride, PVC, has that big chlorine atom sticking off of that. Again, impedes any crystalline structure. If we've got a stiff backbone, that can fold, that somewhat supports crystallinity. Strong intermolecular forces favor, so van der Waals forces, hydrogen bonding, they favor the formation of crystals. Narrow molecular weight distribution also increases crystallinity. So again, in this case, DSC can really be more than that identification tool. It can give you insight into the material to understand more about its molecular structure from a fundamental standpoint. That's something that I think is relatively important. Okay, and there's a whole series of things of what elevates or lowers the melting point of the material. And again, we won't necessarily go through that again. We talked about that a little bit before, but again, both crystallinity and melting point are affected by the structure of the material. And if you've ever heard me talk before, you understand that I'm a big proponent that chemistry drives performance, that it really is all about the chemistry, and that certainly has to do with the molecular structure of the material. Different polymers behave in different ways because they have different structures. DSC provides us some insight into that material. So we talked about how important crystallinity is, and it can be very, very important in performance properties of materials. Okay, we want to understand how crystallinity impacts performance. So higher levels of crystallinity are going to give us, in our molded part, are going to give us better creep resistance. They tend to give us better fatigue resistance, higher tensile strength, stiffer materials. So in many cases, again, we're trying to optimize the crystalline structure of the material through the molding process. Well, DSC is going to help us evaluate that. So for that, we're going to run what's called a heat, cool, heat run. And I've got it again plotted in time. We don't normally plot this in time, but I wanted you to understand how this works. So we're going to heat the sample up at a heating rate, typically 10 degrees C. We're going to control cool it again at that same rate, 10 degrees C. We're going to cool it down. And then we're going to heat it. We're going to heat it a second time. So the first heating run tells us about the condition of the material in which we've received it. So if it's just been molded in its as molded state, or if it comes back from the field in its state as which we've received it. That first heating run and the cooling run, well, that erases all of that heat history. And the second heating run now gives us information about the inherent properties of the material, okay, what the material wants to be, okay? You typically, during the molding process, don't want to try and fool the material, or you want it to be what it wants to be. It has a structure, it has a molecular weight, again, which are going to lead to structure. You want to allow that to happen. So what we're looking at normally in that heat, cool, heat run is we look at the first heating run and then the cooling run, again, by temperature. And on that first heating run, we get our heat of fusion, we get our melting point. On the cooling run, we get the temperature of recrystallization and we get the heat of recrystallization. Then we come back, again, as really part of the same run. We just plot them on two different plots typically. And we get the second heating run. And again, we're measuring the melting point and the heat of fusion of the material. This heat, cool, heat run in particular is going to allow us to assess the crystalline structure of the material, the crystallinity of the material as we received it, as opposed to how it wants to be. So let's see an example of that. So for some materials, we're going to see, as we heat the sample up, we're going to see this nice exotherm, which tells us that the material is forming crystals during the actual DSC run itself. This is a polyphenylene sulfide material, PPS. You can see that immediately after we go through the glass transition, that's right here. Once we go through glass transition, those molecules have sufficient freedom now that they can reorganize themselves. They're not locked in anymore, not as much. And so they can reorganize and they form some crystals. And that's what we're seeing here, is this material forms crystals. When we see that, my immediate thought is, well, that material's been undercrystallized through the injection molding process. The material wants to be more crystalline. Okay, not 100% crystalline, obviously, but it wants to be more crystalline. But the tool used to mold it was probably relatively cold. Perhaps the molder wanted to produce more parts per hour and didn't really focus on crystallinity. Well, that's, again, this tells us that the material has been undercrystallized. In fact, if we look at the heat of crystalline formation, it's about 15 joules per gram. When we look at the melting of all the crystals, both that were there before and those that formed during the test, it's 30. That tells us that half the crystals that are melting during this test were formed during the test itself. The material was only, if you will, half crystallized during the molding process. Again, that has severe implications for its performance property. So this is the first heating run and the cooling run. Again, it erases the heat history. When we come back, and heat it again, because during the test we've control cooled it, we've allowed the material to become crystalline, we don't see that exothermic transition, right? All we see is that roughly 30 joules per gram associated with the melting of the crystalline structure that's there, okay? So again, now it'd be great if all polymeric materials had that exothermic transition, but only a few do. Polyethylene terephthalate, PET, PBT does sometimes, polyphenylene sulfide, polyphthalamide does. Not a lot of materials do. So what do we do then in other cases? Well, in other cases, we run our heat run, and we compare the heat diffusion during the first run, again, as the material was that we received it, or as it was molded, in this case, about 193 joules per gram, 194, to the second heating run. The second heating run is substantially higher, 236 joules per gram. What we're looking for, my rule of thumb is that this number should be 90% or higher of this number, and then I can say that that material was, adequately molded. If it's less than that, in this case, way less than that, that material is undercrystallized. And again, it has implications on the performance properties of the material. Well, that's what we're doing, is comparing it. Now, we've talked mostly about, in the condition of the material, we've talked mostly about the melting endotherms, okay? But let's not look past those recrystallization peaks, because they do tell us something. Again, here's an example of polypropylene with and without a nucleating agent. So a nucleating agent might be used in polypropylene to impart some clarity, okay? Maybe make your potato salad container that you get at the deli so you can see through it, okay? It changes the way the crystalline structure forms. And we can see that there's a pretty big shift in that recrystallization. Now, there wasn't a big difference in the heat of fusion or the melting point of those two resins, but there is a big difference in how they form crystals because of that nucleating agent. Nucleating agent results in smaller crystals and a delay in the crystal formation. The crystals start to form sooner, but they tend to be smaller and more prevalent. We can also get some insight into molding from that cooling recrystallization peak. Okay, so for example, for polypropylene, we can look at where's the set point of our mold. Okay, and based upon the set point of our mold, where are we going to start to get crystal formation, and how is that material going to crystallize? We can by running different experiments, again, isothermally, and again, we're looking at time. So what we're looking at here is, while this is cooling, and you think normally it's going to go in this direction, this is time at isothermal during cooling, okay? And so what's happening is the colder we set this to, the colder our injection molding tool, that's going to be a different way that those crystals are going to form compared if we've got that higher temperature. We're going to get a more slow, uniform crystal formation out of that higher mold temperature. Again, we're also going to get a higher level of crystallinity. So again, this DSC can actually be used to get some processing information. What do we think that material is going to do? And certainly, we can also get information about thermosets. Okay, so by the way, this is one of those times when this graph is upside down, if you will, to how I normally look at it, and exo is down. So as a thermoset material, cured, has cures, or it's cured, so it has crosslinks. That degree of cross-linking is going to change the glass transition temperature of the material. That holds true for thermoset plastics like epoxies or phenolics, or thermoset elastomers like EPDM rubber. Okay, the more cured the material is going to be for thermoset plastics, the higher that glass transition temperature is going to be. And typically, we're trying to maximize that reaction. So again, much like we did with some other test techniques we talked about earlier, we can assess the material and understand how cross-linked the material is by where that glass transition is. Again, it does require kind of establishing some level of what I'll call like calibration curves, things like that. But at a minimum, if you just run basically your undercured material and your fully cured material, you can understand where that glass transition is. And again, you can start to set up basically a time and temperature phenomenon, and you can understand how cured your material is, and make some projections for how long do I need to hold this thermoset in my mold at elevated temperature. Again, the other thing that's going to change is also going to be the heat of reaction. So as we heat the sample up, in many cases, thermoset materials will undergo a reaction. Again, XO is down in this particular case. And so we have this transition. If we have a less cured material, we're going to see more residual cure that's going to happen during the test. If we have a more cured sample, there's going to be less of that. So again, curing has an effect not only on the glass transition, but also on the amount of cure that's left. So what we can do is we can take some raw resin for our thermoset material. We can establish a heat of cure, okay, at say 14 joules per gram. Actually, this is for our sample. We know that our raw resin, has a heat of fusion of 46. We subtract that, we do the math, and we can come up with our cure percentage. Now, typically, you're looking for a cure percentage in thermosets of 90% or above, or 80% or above. I like to target 90, but some people are good with 80. So again, we can get a good feeling for how cured that material is, not only through the glass transition, but actually get a number by looking at the residual cure that's left. Now, not all thermosets react in a way that allows you to use this technique. Rubber does, again, if we're talking about that EPDM rubber, we can do the same type of thing. Now, here we have XO down, but we simply measure our raw rubber, that heat of the reaction. We measure the heat of the reaction left in our molded part at maybe, what we used to do is multiple locations on the part to be able to understand is the part evenly cured or cross-linked, but multiple locations, and then you can do the math and you can find out is your part properly cured to specification. And this again is just the same. This was EPDM, and this is a hydrogenated nitrile rubber material. Again, understanding that, looking at the glass transition of the material, and then the residual heat that's left in the material, heat of reaction. Heat capacity is another test that we can do, again, looking at the condition of the material. Specific heat capacity, or C sub P, that's a fundamental thermodynamic property of the material. And DSC gives us a great way to look at it. So there's two basically different ways to do that. Traditionally, in older pieces of equipment, you can get that heat capacity by doing three separate runs. You run a baseline run, you run a sample run, as well as a calibration run, and you can get then the heat capacity of the material through that process as a function of temperature by comparing those three. Newer pieces of equipment allow you to do that basically all at once, okay? And so we can get that information all at once by looking at the total heat, the heat capacity of the material over a temperature range. So you can understand what it is at different temperatures through that heating cycle of the material. Again, makes it very, very easy to be able to determine that specific heat or heat capacity of the material. Typically, that's done, again, in the new instruments using what's called modulated DSC or MDSC. Test methodology. So we've talked a lot about the information we can gain. Let's talk a little bit about testing now. So DSC can accommodate many forms of samples. Hard solids, powders, even liquids can be run by DSC. So that's why it's very versatile. the important parameters we need to think about when we're setting up an experiment are the type of sample pan, our sample size and shape, the temperature range we want to run, the heating rate, the purge gas, make sure that we do the calibration. That's not really a variable, but it is important in the quality of the data we're going to obtain. So we're going to pick the pan based upon the experiment we want to run. Most pans are going to be aluminum. It's it's an inexpensive material, gets us to the melting point that we need. I mean, the melting point of the aluminum is higher than we're typically going to run. And so most pans are run, or most experiments are run using an aluminum pan. But there are other pans we can use, and we'll talk about one specifically that gives us some different results. We also then have different configurations. They can be open to the atmosphere, they can be sealed, they can be hermetically sealed, they can be pinhole. Again, it depends on the experiment. We could spend more time here, but I think it's most important that you understand there's a variety. And I'll, again, in order to cover a lot of material, I'll let you decide, to kind of explore that a little bit more about what the different pans can do. So a lot of our experiments are run in just simply what's called a crimped pan. Now, you can do this with just a crimped, or you can do this in hermetic. But the two pans, the bottom and the top, our sample goes inside of here. The lid goes on top of here. It goes into this crimping device, and that crimps the pan, closes it shut. And that's how most of the samples that we run are run. Now, again, that's an aluminum pan. Kind of the exception to what you want to do is, well, certainly for OIT experiments, you need to be exposed to the atmosphere. So you either need to run a pinhole, or more commonly just an open pan to do that. And you get different results whether you run an aluminum pan or a copper pan. Copper pan, the copper atoms tend to catalyze that oxidation reaction, particularly in polyethylene and polypropylene, where OIT is run a lot. And so usually that's a benefit, to get that OIT to come faster, because oftentimes these experiments kind of go out. They can go out to an hour, 2 hours. We don't want them to go necessarily that long. That's a lot of instrument time. So the copper pan helps us to reduce that. Particularly useful if you're, I know we used to do it a lot when we had electrical systems, and there was copper present. Then it creates a very realistic atmosphere. So anyway, that's an area where we might use a different pan. Sample mass also is very, very important. Finding the right mass is going to be important. Very, very low masses produce what would be a sharp onset, a relatively narrow peak compared to high mass samples. Okay, we typically are going to be in the 5 to 6 range. That's where we have found that kind of is our sweet spot. It's a compromise between kind of that getting that narrow endotherm, and also getting a good signal to noise ratio. So that's what we have found is kind of our sweet spot. But sometimes we run much smaller samples if we don't have much material. Or if we're looking at transitions that we think are relatively weak, we may run larger samples. But again, 4 to 6 is kind of where we typically run. Sample configuration is important. So you don't want to just throw this large piece in your pan and then crimp it. You're going to get small contact area. What you want is the maximum amount of contact area that you get. So what you necessarily wouldn't want to do is take an injection molding pellet, throw it into the DSC pans, and then crimp it. You're not going to get good contact between the material and the sample pan, which means you're not going to have good contact between the sample really and the thermocouple, which is most important. So again, you want to try and make that. Now that again is another compromise. You don't want to cut the sample up into really small pieces. The experiments get to be rather difficult there. So again, being practical about it, we want to do something where we can, get the material into as much contact with the pan as possible. Temperature range, okay? Just because your DSC runs between -90 and 550 doesn't mean that every experiment needs to be run to those extreme temperatures. So pick your temperatures wisely. That being said, you don't know what you're going to see if you don't go higher or lower. Okay, so again, typically my runs are, depending on the thermal stability of the material, we're going to talk about that in a minute, typically minus 40, unless I'm looking for a transition that I know is going to be present below there, minus 40 to maybe, 250, 300, 350, kind of that kind of range, unless there's a reason for me to go higher. Again, a transition that I know, peak going to be higher. One thing that you want to do at picking the low side temperature, the drawback of starting at room temperature is that transitions that are relatively low, maybe 40 degrees C, 50 degrees C, kind of get lost. You want 2 to 3 minutes of baseline before and after transitions of interest. So you want to have enough baseline, particularly on the low end side, is that you get a kind of what's called a startup hook sometimes in the DSC. So again, choose that wisely. And again, we talked about sample pans. If you're going to go very high in temperature, understand that you don't necessarily want an aluminum pan that might melt in your system. That's going to be very bad. One thing about temperature is that you don't want to decompose the samples in the DSC cell. The more decomposition that you undergo in the DSC cell, the more contaminated the thermocouples are going to get, and you're going to get poor contact. You're going to see your signal diminish. You're going to see your results get wonky. So again, you don't want to take a material through decomposition. So things like polyacetal, for example, you don't necessarily want to take that above 275, something like that. PVC is a great example. And I had somebody, I was working with a client who came to me and said that their DSC was giving them problems. What I came to realize was that they were taking PVC, heating it through decomposition, which generates HCl, and that hydrogen chloride just kind of chewed up the inside of their cell, and they had to replace the whole cell. So again, one way you can do that is to run TGA first and understand where the breakdown of that material is, whether that be decomposing to dangerous species or simply giving off stuff that's going to contaminate your cell. TGA can be a big help with that. Heating rate, again, also is going to affect that. Again, you're looking at sensitivity and resolution, just the same kind of way you were looking at weight. So, if we move up as we get faster and faster, we're gonna see that our melting point is going to shift. And so faster heating rates, they increase sensitivity, but they come with the expense of resolution. So typically we find that 10 degrees C is a good place to start. Probably 98% of all our runs are run at 10 degrees C. When you think about the cooling rate, think about what you want to accomplish. If you're doing that heat run to look at crystallinity, well, the heating rate and the cooling rate should be the same. If you want to understand more about what happens when you quench cool a material, well, then you might want to quench cool it. Some of the DSCs out there have quench cool abilities. They can cool relatively rapidly. Otherwise, you can always drop your sample pan. You can open it up, drop it in the liquid nitrogen. That's certainly going to quench cool it. That's not very common. Normally, our cooling rate is the same rate as our heating rate. Purge gas. Again, you should always use purge gas during any type of experiment. Important that it's pure. You want dry and inert gas so that your gas is not going to react with the sample. Again, nitrogen, helium. Most cases, you can use argon too if you have an argon tank. And then, air, oxygen if you're doing oxidative induction experiments. And again, the quality of the instrument is also going to change the performance that you get. Again, most DSC systems that are out there are very good. It's just how good, and so certainly the Q1000, which is the TE Instruments, that's an older model. That's their more expensive unit, but it gives you better resolution, better signal quality. Okay, so again, not that the Q10 gives you bad signal. Again, it's just what you're looking for to understand the instrument you have. Calibration, very, very important. You want to get trustworthy, accurate results. That means you need good calibration. You need to calibrate both temperature, so what the temperatures are, as well as the heat flow. Okay, so typically temperature calibration, I like to see 3 temperatures. maybe room temperature. So you leave the pan open, you have a calibrated thermometer in the laboratory, and you use that. Then you use indium, which has a very set melting point, and use zinc, again, very set melting point, pure samples. And you can, again, create a calibration curve for temperature. You also want to use heat flow, and again, you can use those same metals. They have very reliable melting point or heat diffusion, and you can look at that. So again, both those calibrations. I like to see calibration monthly. Quarterly is okay. I think the standard actually calls for annual, and that's just way too far apart. You don't know if something has gone wrong with your system. In addition to being calibration, it's a running calibration. After that calibration, right before and after calibration, I typically run some kind of system check. I run other materials that I retain, kind of quasi standards, in order to make sure that my DSC is operating right. Thermogram artifacts. Again, I talked about that startup hook. There you go. You don't necessarily want to have a transition that's right through there. So again, pick your startup temperature wisely. Again, many different types of material events can be seen by DSC. There's a lot of more than we can cover in this time period. I did want to talk a little bit about artifacts, and that's some of those transitions that you might see, or features in the thermogram you might see, I should say, that aren't really associated with the sample itself. So there's a lot of them. And you want to be able to recognize them. We see, once in a while, we see like an electrical blip, an electrical spike, and that can look something like this. This can also be mechanical. If the sample actually moves, you can actually see that sometimes. The sample moves on the pan because it pops if it's got a lot of water in it, and the water comes off, kind of like a kernel of popcorn. Sometimes it can move. Again, sample movement in the pan, that this and this can look alike. You can get a chemical reaction. This can also be decomposition, can look a lot like that. So again, understanding there's a power spike, understanding that some of these, and if you have an anomaly, I mean, this can look a lot like a melting endotherm. It's best to rerun the sample and see what you get there. So again, getting the best results. Again, avoid these pitfalls. So you want to have a good understanding of the material and the objectives of the DSC analysis. What do I want to obtain from it? Okay, is it material identification? Is it understanding crystallinity? What am I trying to do here? You want to make sure that you have good, reliable calibration. You want to minimize contamination. So your sample prep area around the DSC, just like it would be for any analytical piece of equipment, should be clean. Minimize that sample preparation, contamination. Also, how you load the sample in, you don't want it to be one big nugget, if you will. You'd like it to make more contact with the bottom of the pan. Again, understand whether you have residual moisture or solvents in your material. Sometimes it's not possible to get rid of, but you need to understand then that they could interfere with that. Have a good concept of the heating lag, the thermal lag associated with the cooling and heating rate and the sample mass. And again, you're balancing resolution versus sensitivity there. Processing errors. Again, practice going over thermograms in order to do that, in order to look at that. I get a lot of questions about what's the best way to measure glass transition, because it's again, DSC measures it so importantly. Unfortunately, DSC is probably the poorest of the other techniques. You can get glass transition off of thermomechanical analysis as well as dynamic mechanical analysis. DMA is really the best way to look at it because it's directly measuring what glass transition is, the mobility of the molecule. In DSC, you're measuring heat flow, which is we'll call it an artifact or a side effect of that molecular freedom. So you're really not measuring the what's going on directly during glass transition in that freedom of the molecule. So again, you can see some differences sometimes if people report glass transitions by different techniques, DSC, TMA, DMA. Understand that can be inherent into the test technique itself. And don't forget, okay, DSC is a bulk technique. Again, it doesn't sound like it. You use 4 milligrams, but you're not analyzing necessarily, some micro material. Okay. And by the same token, understand that if you analyze a pellet or a section of a part, understand that if things aren't uniform, you're not necessarily going to get representative results. So sometimes sampling at multiple locations on a part or running multiple pellets is the way to go. Again, you just need to understand that. Instrument error in terms of measuring temperature can be, plus or minus 0.5 up to 1 degree. Our instrument's a little lower than that, probably closer to 0.1 degrees C. But again, understand your instrument and what your thermal reproducibility is. Might not be a bad idea to run the same sample a few times so you understand that. Thermal events can be altered by a thermal lag. DSC tells you what is happening at the temperature it happens at. Okay, so use caution when extrapolating back to room temperature for stability or interactions or reaction kinetics or things like that. Don't overinterpret the data. Again, sometimes there's noise in the sample. You may not analyze, you may not get to understand every small blip that is present in the thermogram. Verify any anomalies you see. Like I said, if you suspect that the material has been degraded, then DSC gives you that warning signal, but may not be the best indication of that. Materials with similar melting points can't be distinguished. So again, just like FTIR, it has its weakness. Nylon 6 and PBT melt at the same time. Polypropylene and polyacetyl copolymer melt at the same point. So again, that's why a series of test techniques, FTIR, DSC, TGA, all go very well together to complement each other. Again, we've talked about this. Keep that area clean. The simplest analysis is generally the best. If you're going to interpret results, you really should have a good understanding of how the analysis is done by having run some tests. That's my opinion. You need experience to look at the interpretation. Again, run your materials that you know what they are and characterize them. Create a library of your DSC results. Okay, support that with a knowledge of organic chemistry, and again, use those complementary test techniques. I think at this point, I'm going to take some questions, and then if we have time after questions, we'll get on to the case illustrations. Okay, Tenmaya?
Thank you very much, Jeffrey, for this great presentation. I hope it provided good insight to our participants regarding this interesting topic. Now, before we start our question answer session, we would like to gather some feedback. Ladies and gentlemen, please check your chat box. I've sent you a rating card link. Please click on that link and provide us with your valuable feedback. You can also add your additional comments or suggestions which you would like to hear from a special chem. Now I will wait for 2 minutes for our participants to fill in the rating card, and then we'll start with the question answer session. Ladies and gentlemen, please do fill in the rating card. It helps us in improving our services. Also, if you finish filling up the rating card, you can drop your questions in chat. I hope everyone has filled in their rating card. Let's begin with our question answer session. For that, I have activated raise hand button. You can use raise hand button to ask live questions to Jeffrey, or you can send your questions through chat. So Jeffrey, in the meantime, we are getting some questions. You can continue with the case studies.
Okay, sounds good. So here we had some sleeves from an automotive application that cracked after assembly. Sleeves were specified to be injection molded from a 20% glass fiber reinforced PBT resin. DSC on the first heating run on the reference material produced results characteristic of PBT. We had a melting point of around 224 degrees C. That looks good. Analysis of the failed sleeve showed a significantly lower melting point, 219. Again, that 5 degrees C is that's a big difference. I'd be looking for any difference greater than 2 degrees. It's kind of, again, waving that red flag that something might be wrong. The failed material transition was also broader. Overall, the results suggested molecular degradation of the failed sleeve material. Degradation then was supported by the second heating run. The failed sleeve showed basically an additional differences relative. We're seeing that PBT in many cases exhibits, this is our reference, exhibits this on the second heating, this kind of bimodal melting endotherm. You see that that's not really present there. Again, our melting point is here just about, it's almost 5 degrees lower. We supported that by melt flow rate. And again, that did, again, support our conclusion that we had undergone molecular degradation. Here we have a plastic nut. It's stripped out during installation. The failure was limited to one particular production lot. This was specified to be a black pigmented 40% glass and mineral reinforced nylon 6,6 resin. We measured moisture content, but the suspected parts were high in moisture, so we got a softening effect through the plasticizer. But again, not a consistent trend. We didn't really think that was going to tell the full story. DSC though gave us some additional information, and that showed the presence of polypropylene contamination. And that, again, here's our transition associated with the nylon 6,6. We see this additional endotherm associated with the polypropylene, which tells us it is contaminated. That polypropylene is going to be a little softer material, probably not going to be very miscible with the nylon. So it's probably going to lack the glass and mineral filler. It'll be softer, going to allow that nut to strip out. And so that again is what we're identifying there. The fact that we've got propylene contamination in nylon suggests that we've got a post-consumer recycled material, possibly maybe from carpets. Our next example is some molded plastic couplings exhibited abnormally brittle behavior, specified to be a custom compounded glass filled nylon 612. Inspection of the molding resin used to produce those parts showed some, those bad parts showed some differences in the appearance of the individual pellets. So we grabbed some individual pellets. The control molding resin that we had from our retained, again, looks like a nylon 612, melting point around 218 degrees C. One of the discrepant pellets looked a little different, had that same melting point, but also had a melting point about 165. Again, tells us that that's likely contaminated with polypropylene. So we've got non-homogeneous pellets. We ran another one, and this time our nylon 612 was contaminated. That particular pellet was contaminated with nylon 6,6. So again, major amounts of contamination, again, that are going to create problems. DSC did a great job of identifying that. FTIR really didn't identify that very well. DSC played a key role. Here we had some failures in some small engine gas tanks while in service. They were cracked, which resulted in leakage of the gasoline, which is a hazard. The two halves, the upper and lower, are hot plate welded. And there was a material conversion, which was touted as a drop-in. One of the high-density polyethylene resins was discontinued. And so it was said, well, we have this drop-in resin that works. We can see fracture surfaces there, limited macro ductility, some stress whitening, origins along the exterior edge of the wall. Fracture surface, again, slow crack growth, creep rupture mechanism, FTIR, just so that, basically they're both polypropylene. There were no signs of contamination or degradation by FTIR. Then we ran some DSC, and we found that the fail tanks had a melting point that was consistent with high density polyethylene. They were well crystallized. These are the second heating run, so they had good heat diffusion. What we did find out, however, that these are not drop-in. The new material had a relatively high level of crystallinity. If you look at this on the second heating run, our material has a heat diffusion of 212, and our original material 179. That would be, if you were talking about density of high density polyethylene, this is probably a 954, 956, and this is a 948, 947 probably. That kind of difference is huge for high density polyethylene. Again, that they're going to give us different levels of performance. This material, higher crystallinity, is going to be stiffer, but under that welding process, it's going to have more formed in stresses. So that's, again, DSC gave us a good indication. One more piece of information, again, some books that I find helpful. If you want to be able to look, particularly like the book by Mike Seppi. Mike was just a guru in thermal analysis, particularly the DSC. So if you only buy one, that's the one I would buy. And that kind of brings us back to questions.
Thank you, Jeffrey. Dear participants, please do not hesitate in asking your questions. We still have a couple of minutes left. If you do not have any questions, then we'll move forward to close the session. Well, thank you everyone for joining this course. In case if you have any questions which you would like to ask, please feel free to send us an email and we will include them in question answer transcript so that Jeffrey could respond to them. And if you wish to receive the question answer transcript, please make sure that you fill in the rating card. Thank you once again, Jeffrey, for this wonderful presentation. On behalf of Special Chem, I would like to thank all our participants for attending this online course and making it a success. We look forward to welcoming you again on a Special Chem online course. Thank you and goodbye.